would like to discuss the topic of goodness of fit. And one of the techniques is to apply the chi-square test while comparing a frequency distribution to a probability distribution. This is strictly applicable to the discrete distributions. However, for continuous distributions, sometimes we apply it in the limiting case. There are other methods of uh, inferring the goodness of fit. There are also the graphical methods and computational methods. So a class of methods deal with the comparison of frequencies from the data and frequencies generated by the theoretical model. This is applicable to discrete distributions, uh, and there are methods which compare the cumulative probabilities um, from data and from the model. So there are numerical methods like the Kolmogorov-Smirnov test, and there are graphical methods which are very interesting transformation of the numerical comparisons on a picture. So uh, let's talk about the chi-square test. So the only topic I would like to discuss here is the chi-square test for frequency distributions. This is from the chapter 3 of our reference book by Professor William J. D. Corsi. And also from chapter 7, there are good examples um, in the book by Professor Murray Spiegel and Larry J. Stephens. So here is a review that we talked about the frequency distributions, and generally it is discussed in the very early topics of probability and statistics course. So we start from the uh, data which comes from the experiment, and the data exhibit the random variations. We then develop the frequency distribution and the probability distributions. And then in the course, we talked about the probability distributions, uh, which are which are statistical models based on assumptions like the probability of success and probability of failure, and then we generate the estimates in binomial distributions. So they exhibit the predictable variations due to the fixed properties, which are then modeled in a mathematical equation. So we found the candidates of discrete distribution like binomial and Poisson, and they represent the probabilities of individual events. So probabilities are written as probability x equal to x, where x can take on the discrete values. However, the other set of probability distributions are of continuous type, like exponential, normal, log normal, and there are the Weibull distribution, and well, there is a good gallery of those distributions. There is one fatigue distribution, and the Laplace distribution, and many other distribution. I think the list goes on and on, and it exceeds a number 70. So, however, they represent probabilities by a probability distribution, probability density function f of x, which needs to be integrated between the limits of interest like a to b. So when it is integrated, it gives us the probability that the value of x continuous variable lies between A and B. So with this, we can start learning the goodness of fit. The objective is, can a frequency distribution be approximated by a probability model, and how adequate it is? Therefore, we define hypothesis, and hypothesis must be defined about a significance level. And then there is going to be a calculation of test statistic, which is going to give us the basis for comparison. And then we have to define the degrees of freedom. The degrees of freedom in this case are defined as n. This will be defined with a bit modified, and for the number of classes, we will see that -1, it is the condition derived between condition which is fixed between the frequency distribution and the distribution of frequencies coming from the model, and then -k, which is the number of model parameters estimated from the data. Because for model generation, we are going to utilize our experimental data from which the distribution was developed. And then we will make the inference. So let's look at the test statistic. So we will go for the hypothesis definition. The null hypothesis is data resembles with a given model, and the alternate hypothesis that the data does not resemble with the given model. So the model is adequate to represent the data, which is null hypothesis, and the other alternate hypothesis can be defined accordingly. So we define a metric, a test statistic, which is the difference between the observed frequency and the expected frequencies. This O values will come from the data, and the E values will come from the probability model, and square of it, which is our way to define the variation, and divided by the expected frequency. And since there is the I subscript, so it suggests that it is for individual classes. So where I varies from 1 to the n, I call it the number of revised classes or revised number of classes. So it is going to be slightly different from the number of classes in which we have initially distributed the data during the process of frequency distribution generation. So the one condition is that the total frequency in the observed set and the expected set, it must be equal. That's why the -1 appears in the calculation of degrees of freedom. Okay. Then, like we did earlier in the definition of chi-square test in the earlier session, we will define a significance level, which is defined generally in the upper tails. So at the significance level, we will get a critical value of chi-squared. So this will be again for some degrees of freedom and a significance level. And then we will compare the calculated value and the critical value. And if the critical value, which is at some level of significance, is greater than the calculated value, which means our calculated value falls over here where I am pointing with the virtual laser pointer. If it falls over here, it means the data can be adequately represented by the statistical model. So we know the chi-square distribution, it has a variable shape due to the degrees of freedom. And I introduced the chi-square table in the earlier demonstration. So here is a recap that we look for a degrees of freedom, and we have to define a significance level. Then the critical value can be adopted from the statistical table. Now let's look at the example fitting a Poisson distribution to the data. So There is the example. The number of cars crossing a local bridge was counted for 40 successive 6-minute intervals from 1 to 5 a.m. The numbers can be summarized as follows. So the number of cars in 6-minute interval. So the frequency distribution has been generated. This represents the variable R, so which is discrete variable. So in a 6-minute interval, the person count the number of cars which were crossing on the bridge. So it happens twice that in 6-minute interval, no car crossed the bridge. Likewise, this can be interpreted that it happened 7 times during that observation, that in 6-minute interval, uh, one car crossed. Then it happened 10 times that two cars passed the bridge. So this data was generated. It's a discrete variable. So this is the observed frequency, our O or FO, which is going to be written. Okay, so from this data, we can calculate the mean value, the mean number of cars that pass through that cross the bridge during the 6-minute interval. So we find with the mean value calculation. Okay, well, this should be Ri. So mu value is calculated 2.875. These are the number of cars when the time interval was 6 minutes. And if we calculate the rate, so it is mu value divided by 6, so 0.4791 cars per minute. So with this calculated value and the mu value, we can use the Poisson formula, which requires a mu value, and R values can be taken from 0 to any higher value at which the probabilities are significant. So with this formula, we can generate the probabilities. Poisson distribution seems to be one parameter probability distribution. So this is the parameter which we have calculated from the data. So with this formula, we will calculate the probabilities of R at R values. Probability R equal to Ri. This can be generated by the Poisson formula. And to generate the expected frequency, each probability will be simply multiplied to the total number of cars that were observed in the whole uh, 4 hours activity. So 1 to 5. So I found that these were 40 cars, right? So, yes, this is where 40 cars. So here it is. Let's see this calculation in a Microsoft Excel sheet. Okay. Okay. So I have this data over here. Here is the variable Ri. Here is the R variable. So F frequency. So I can calculate very quickly that this is equal to R times the F value, and this needs to be calculated for all the R values. So I got the total, and the mu value is equal to the sum of Fi times Xi or Ri and divided by the 40, this value. So it is 2.875. Lambda value is optional to be calculated. If I would like to generate the estimates of probabilities, so in Microsoft Excel, I can use the Poisson distribution, and I have to have the variable value and the mean value. I can pick it from C$14. so that it remain fixed. And I'm looking for the individual probabilities. So probability mass function, and that's it. And similarly, this will be generated for all of the values, and for all the values greater than 8, it seems that there is going to be a very, very small contribution, and the contribution can be considered as it is the total is 1 minus sum of all the probabilities of values from 0 to 8. So the remaining event contains less than 0.3% of the probability. So it is fair enough to consider probabilities up to this level. Now, let's see the comparison. If we go for the graphical representation, so the observed frequencies are shown by the blue bars, and the uh, predicted values from the model, they are represented by the red bars. So at some stage, it seemed reasonable that the distribution has been modeled. However, there is no such numerical metric defined up to this point. Therefore, let's define the numerical metric and calculate by the chi-square test. So we go for the calculation of revised classes. There is a rule of thumb while applying the chi-square test, that near the tails towards the upper side and towards the lower side, the differences in the observed and predicted frequencies could be larger. Therefore, there is a rule of thumb that if the expected frequency is less than 5 in a class, then it should be merged with the class adjacent to that. So we see here that the observed frequency is less than 5 over here. So we will merge the class with variables 0 and 1, so that the number would become larger than 5. And likewise, the classes which are to the upper tail, so these classes must be added, so that in every class the individual frequency becomes greater than 5. So we go for the revised classes. So like class with variable 0 and 1, they are added to give us an expected frequency to 8. And likewise, all the classes, they are merged to give us a frequency 6.45. Then we calculate the metric for chi-square test. And it leads to a value. Well, the chi-squared calculated value is 0.23 in this case. We define the two hypotheses. Null hypothesis, the observed frequency distribution is consistent with the Poisson distribution, and alternative hypothesis is contrary to null hypothesis. So we have the calculated value 0.23. The degrees of freedom are we have 1, 2, 3, 4, 5. The 5 classes. So the calculation was performed on the revised number of classes. Therefore, this number is 5 minus 1, and this minus 1 is that the mu value for the generation of Poisson estimation, Poisson estimates, that was developed by through the data, or it was generated from the data. Therefore, the degrees of freedom are 3. So if we test it at 5% level of significance, so the value is 7.81. So the calculated value is less than the critical value. Therefore, we can infer that the null hypothesis cannot be rejected, and the observed frequency distribution is consistent with the Poisson distribution. Let's see that one more time on the graph. Well, our calculated value is much smaller than the than the critical value. Therefore, we can say that we can accept it. So here it is. I found that at 3 degrees of freedom, it is 7.81 at 5% level of significance. So that's the way we carry out these calculations. There is another example for fitting it to the normal distribution. Chi-square test is strictly applicable to the discrete distributions. However, we can approximate continuous distributions to discrete distribution to apply the chi-square test. So we have the example that thickness of a particular metal part of an optical instrument on 121 successive items from a production are given. So earlier we generated the frequency distribution and we developed the expected frequencies. In this process, we calculated the mean value and standard deviation from the data, and mean and standard deviations are required to generate the estimates from normal distribution. During this process, we utilize the z-square table, and there is a demonstration for generating the theoretical estimates of probabilities at this link, and this was introduced earlier as well. So we know the procedure of generating the expected frequencies for a normal distribution. So here are the glimpse of calculations that we define the lower limit and the upper limit of classes. Then the x for a given x, which is the class mark of a class, and the observed frequency and relative frequency. We calculate the mean value and the sigma value, and then we go for the corresponding the lower limits and the upper limits in the z variable, and then we generate the probabilities. In this process, we have to carefully look into the numerical table of z-score, and then we calculate the expected frequency. Here the expected frequencies in few classes near the tails, upper and lower. This is the lower tail. They are less than 5. Therefore, we have to merge the classes. And likewise, we have to merge the classes at the upper end of probabilities. So we go for the revised class frequencies. So towards the lower end, first 3 classes need to be merged, and towards the upper end, the 3 classes must be merged. And then we calculate the chi-squared value. So here it turned out to be 3.77. And for the degrees of freedom, we have 5, 1, 2, 3, 4, 5, and -1, which is the one condition, and the 2, that 2 parameters, mean value and standard deviation, they were calculated from the data. So the degrees of freedom are 2, and at this level, at these degrees of freedom and 5% level of significance, we have the critical value 5.99. So again, the critical value is larger than the calculated value. So therefore, our calculated value falls within the confidence interval. Therefore, we cannot establish a sufficient justification to reject the null hypothesis. We have to accept it, and this data have been adequately represented by normal distribution about the mean value and standard deviation calculated from the data. Now there is the third example that I selected to be demonstrated at the end. So Professor De Corsi introduced that one at the very beginning of the section. So the last one in this session. So a die was tossed 120 times with the observed frequencies shown below. Test whether the die shows evidence of bias at 5% level of significance. So the bias is to be inferred at 5% level of significance. So the observed data is given here. The one dot shows up 12 times, two showed up 25 times, and we have these numbers generated when it was tossed 120, when it was rolled 120 times. So null hypothesis that it's a fair die, which should produce probabilities 1 by 6 for every outcome. And the alternate hypothesis is that all results uh, are not equally likely. So in this case, we know the expected frequencies should be 20 for each outcome. And if we calculate the chi-squared value from its formula, it turned out to be 12.50. So let's see. So here we have the degrees of freedom 6 minus 1, which is 5. Since we have not generated it about any distribution, uh, so we have the 5 degrees of freedom, just with the one condition uh, that the sum of frequencies in observed and the expected must be equal. So these numbers should generate 120, 120 on both the columns. Okay, so the critical value uh, is 11.70. So 11.70 over here, and chi-square calculated is 12.50. So this time the value from calculation falls in the significance region, in the upper tail region. Therefore, we cannot accept the null hypothesis. We cannot, rather, we cannot reject the alternate hypothesis. We have to accept the alternate hypothesis that this die should not be considered as fair one. Its outcomes are not equally likely. So that's the way we interpret the chi-square test results. And there are other methods to go for the goodness of fit. Like we have only considered the method in which is applicable to discrete distributions, and we have not mentioned the graphical methods which intelligently incorporate the probabilities in such a way that if you select a particular probability paper, then the data shows up as a straight line, which is the indication that the data belongs to the distribution for which you are using the particular paper. So I close this discussion with the quotation by the uh, honorable statistician Samuel Carlin, that the purpose of model is not to fit the data, but to sharpen the question, that it guides you to a new horizon and a new way of looking at the problem. Okay. Thank you very much.